Hey everybody, welcome back to another round of physics, and yeah, let's get going. As the title of the slide would suggest, let's spend a little bit of today discussing charges, and in particular, I'm interested in thinking about how would you go about determining that there are two different types of charges, and maybe how would you go about starting to get an idea about the forces between charged objects. So let's get going. So first off, I have for you a tape demo here. And I've always found this interesting when I found it in this book, that yeah, it does work, and it's kind of a reproducible way of making sure that you separate charges in the same manner every time. So let's go ahead. I've got a video here and I'll walk you through. What's going to happen is that I've taken two pieces of tape and I've put them on top of each other. And I've just labeled one top one and bottom one. And now the process of ripping them apart, I have separated the charges in a consistent manner. What I mean to say is that the top piece of tape has one particular charge and the bottom piece of tape has the other. Now you notice that that attraction still exists, right? That bottom piece is attracted to the top piece. Oop, accidentally dropped it there. Sorry about that. So let me go ahead and place the second one so they're separated. Now here's where we start kind of getting a little bit more fancy. I've got a second set of tape. Again, bottom one, two, and top two. I will separate those again in a consistent manner. And now let's go ahead and look at the interaction between the top one and bottom two. You notice that those are attractive. And let's check the other side. Notice that the bottom pieces repel. Right, to the point where it keeps sticking to my hand. Can't get them to touch. Well, what about the top piece? So now let's take a look at the top pieces. And again, if I put the two top pieces next to each other, they don't want to touch. Well, what about if I move over to the bottom side? You notice that the top from the second set is attracted to the bottom of the first. Yeah, there we go. So right away, we start getting a sense of there are two different quantities involved. You say, how is that? Well, I'd say that we have two different interactions. Oops, excuse me. In fact, we could probably set up a little table. We could say the top one and the bottom one, and the top two and the bottom two. So representing the two different pieces and whether it was on the top or bottom. And you notice that, of course, if the top and top, we notice one type of interaction, particularly a repulsion. And the same thing, if we had a bottom piece and a bottom piece, again, we notice that that is a repulsion. Conversely, if we have a mix and match, that is a top and a bottom, and it doesn't matter if it came from the first set or the second set, as long as we have a top and a bottom, we get attraction and attraction. Okay? So we could kind of flip this on the other side. We say there must be two different quantities because we get two different types of interactions. Now we could go further. Now that we have a way of separating those two mysterious quantities, say top and bottom, okay, now we can go and start looking at other objects. Okay? So let's go ahead and do that. So again, I've got my top and bottom pieces still on the holder. And now I'll take a balloon and I'll just rub it. And again, I have no idea what the balloon is going to end up with. I'll use my bottom and top pieces. So again, notice the balloon is repelling the bottom piece and it attracts the top piece. Right? So based on our chart, when we are doing with the two different pieces, we can now say that the balloon must have this bottomness, if you will. it has the same characteristic as the bottom pieces of tape. So now you've got this way of separating out, the charges, the bottomness or the topness, based on the interaction with the tape. Okay? Now, of course, we don't call it bottomness and topness. We arbitrarily say, okay, these are opposite things, and we'll arbitrarily say, okay, we'll call one positive and we'll call one negative. So let's now go ahead and start thinking about how we might be able to measure the force between a top piece of tape and, say, a bottom piece of tape. How would we go about starting to measure those forces? And one of the historical apparatuses is called an electroscope. And the property that I need to discuss real fast is this, conductor. Okay? When we say that a material is a conductor, what do we actually mean? Yeah, go ahead. Take a second, pause the video, see if you can come up with a material. When we call a material a conductor, what does that actually mean? You got it? Yeah, good. So when we say a material is conducting, what I will say, how I will define it, is that it allows charge to move easily through the material. And what do we call a material that does not allow charge to easily move? Yeah, good. We call that an insulator. Now, for the purposes of this class, we will assume that objects are perfect insulators and perfect conductors. And we'll go even a little further than that. For a conductor, when we place some charge on it, we will assume that that charge instantaneously spreads out. So I needed that little bit of material information. And let's go ahead and watch the video here. I'll go ahead and take a glass rod and the wool, and I'll go ahead and rub the glass rod on the wool. Okay. Now we know that we're separating these charges. And now what I'll do is let's go ahead and touch the glass rod to the sphere. Now remember, the sphere is conducting, so I've deposited some charge onto the sphere. Now because it's a conductor, that excess charge rapidly distributes through the length of the sphere and the rod, and by contact down into these aluminum leaves. And now you see, way down at the bottom, you can see those aluminum leaves have separated. By using the electroscope, knowing the mass of the aluminum leaf, and measuring directly the angle, we can infer the force that the second aluminum leaf exerts on the first. Okay? Now, so we have that idea. Okay? Now it's just a matter of repeating the experiment. Imagine for a second that I took the glass rod and I charged it up, say, for half a second. I do the experiment, I measure the angle, and I figure out what the force is. Then I discharge everything. I remove all of the charge from the electroscope. You say, how could you do that? One way is just touch something metal to it, right? If I discharge using, something like a pie plate. Yeah, you see that? Right? By touching the pie plate to the electroscope, I then move charge to the pie plate, and then I can dump it somewhere. I can do it again and dump it, and do it again and dump it. Okay? Generally, this procedure, it would be something, you could do it by connecting the pie plate to the ground. Okay? That dumps all of the charge away. Okay? So then the next thing you could imagine me doing, I charge up the rod for 2 seconds and do it. and I measure the angle between the leaves, and I go through and calculate it. And then I discharge the electroscope. Maybe I do it for a half a second, okay? Or maybe a second and a half, right? So what you really need is some consistent way of getting charge. Now this, of course, this is, very crude, but theoretically it could be done. The length, the amount of time that I spend charging up the glass rod is that would mean that there's proportionally more charge, which means I deposit more charge on the electroscope, and so that gives you an idea. Okay? Pretty cool, huh? Yeah, good. Okay, so now we've got an idea about how could you get a sense of that there's two charges. We have a beginning idea about how could you find a relationship between the amount of charge and the force exerted by that charge, right? So that's a second piece. Let's go ahead, let's think about one more piece, and then we'll call it quits for today, okay? I call it the Swiss wall. So let's go ahead and take a look at this demonstration, right? I've got a balloon, and again, I'm gonna charge it up with the wool. There we go. So we know that this balloon is getting some degree of bottomness to it. Now, right? Yeah, but wait a minute. First of all, I'll pause it and I'll say, now bear in mind, you say, well, this isn't surprising. I say, no, wait. I did not charge up the wall, right? I only charged up the balloon. I didn't do anything to the wall. The wall was neutral. Okay? I didn't do it. It was perfectly fine as is. I didn't do anything to it. Okay. So first of all, we have to have this idea about why did the balloon stick to the wall? Can we come up with some sort of way to explain why that happened? Okay. Second piece, of course, here's the other cool piece about it. Let me flip the balloon over. And now, what? Yeah, okay. So take a minute, pause the video here, and ask yourself, see if you can come up with two things. Number one, I didn't do anything to the wall, so why is the balloon sticking to the wall? And second of all, completely different idea, when I turn the balloon around, why doesn't it stick anymore? Yeah, you got it? Yeah, good. So here's a distinction that we need to make, okay? And I will try my best to be clear about this distinction, okay? There is a big difference between no charge, okay, and no net charge. I'll say that again. There's a big difference between no charge and no net charge. You're all familiar. The wall, for example, is made out of atoms. Okay? For simplicity of drawing, we'll say that, you've got a proton, you've got an electron whizzing around. In fact, I won't even call it E. You've got a proton, you've got an electron whizzing around. Okay? And so there is no net charge. It is neutral. Okay? But now here's the thing. I have charged up that balloon. Let's say I've charged it up with some negative charge. So when I bring that balloon into contact or very close to the wall, which has both protons and electrons, okay, based on what we've observed in previous parts of this lecture, what will the electrons in the wall want to do? Yeah, you got it. Right? We know that like charges will repel. So if I bring this negatively charged balloon close to the wall, it will repel the electrons in the wall. It'll push them away just ever so slightly. Right? Okay. Now, we think of the electrons as moving. Usually with the wall, something solid, we think of those protons as being locked into place. So really, when we bring that balloon in, put this balloon, and I'll say this is the wall, okay? When we bring that balloon in, we're really repelling the electrons in the wall. Just a little bit. We're not ionizing or removing the electrons, ripping them from the atoms that make up the wall, but we're just pushing them off to one side. Okay? Well, what does that mean? That means that our balloon, which is negatively charged, is slightly closer to the positive charges in the wall. And that is enough for the balloon to stick. Okay? Pretty cool, huh? Of course, there's nothing special about that. If I had brought in a positive charge close to the wall, well, what would happen there? Well, that positive charge will attract the electrons in the wall, and so it will pull those electrons just ever so slightly closer to the balloon. But that little difference is enough to cause, again, the balloon to stick. Okay? So it doesn't matter if we charge up the balloon as a positive charge or a negative charge. When we bring it close to a neutral object, for a wall, for example, the ceiling, it will force the electrons either closer to or further away, exposing a little bit of the charge that will allow it to stick. Okay? This process, of course, if I move the balloon away, right, the wall will become neutral again. So this is not a permanent separation of charges. This is a temporary separation of charges. And so you could call this an induced polarization, or if you prefer, an induced dipole moment. That's more the technical term that will make more sense later. So then the other question, why is it when I turned the balloon around and stuck it back to the wall, it didn't stick? Yeah, you probably got it. Remember, right? What's the balloon made out of? Yeah, rubber, right? And rubber is an insulator. Good. Notice I was very careful about only rubbing one side of the balloon. In other words, I deposited charges only on one side of the balloon. Okay? And because the balloon is a fairly good insulator, it's rubber, those charges essentially stay on that one side of the balloon. They are not free to move around. They stay localized, if you will. Now, for completeness, you can think of induced dipole moments. Those are temporary separation of charges in an object. But there are also situations where you have what's called a permanent dipole, a permanent separation of charges in an object. And I believe this is primarily due to the structure of the object, or maybe more specifically, the structure of the molecules from which the object is made. Some examples for you, and I've got some Louis dot structures here, but for example, water or hydrofluoric acid, ammonium. So, for example, what happens? Because of the covalent bonding between the hydrogens and the oxygen, and I believe the electronegativity or the electroaffinity of oxygen, I don't remember the exact term, the oxygen ends up holding on to those two donated electrons from the hydrogens. And so you end up with a slightly more negative charge on the oxygen side of the water molecule. Similarly, you end up with a slightly more positive charge on the hydrogen side of the water molecule. And that permanent charge separation causes a permanent polarization, or a dipole moment. Similarly, you have it with ammonia, you have it with hydrofluoric acid. Okay? It's that sharing causes one side of the molecule to be more negative and the other side to be more positive. Okay? And this tends to happen, for example, with a lot of acids. Okay? Cool. Okay, I'll leave it there for the discussion, but keep chewing it over, keep thinking about it, bring questions to class, and yeah, we'll just keep going forward. Hey, I thank you for your attention. Have a good afternoon. Keep up the good work. I'll see you next time.